If you're preparing for roles like data scientist, machine learning engineer, or AI engineer, this is a topic you can't afford to miss. Time series analysis is what powers weather forecasts, stock predictions, and demand planning. It looks at data over time to predict what's happening next. And in this video, we will introduce you to the foundational concepts of time series analysis and sequential data. You will learn what time series data is, why it's important, and how it's used in real-world applications like weather forecasting, stock market predictions, and even IoT analysis. We will break down key concepts like trends, seasonality, and noise, and explain how they relate to popular forecasting methods like ARIMA, auto-regression, and exponential smoothing. This video is part of our AI, machine learning, and Agentic AI job-oriented program where you'll not only learn these predictive techniques but also gain hands-on experience in AI, GenAI, and more, helping you land high-paying roles in the AI space. Just like our successful trainees Debashish, SD, and Srija, who secured high-paying jobs after completing this program. And don't forget to sign up for our free 90-minute masterclass on how to land your dream job in AI, machine learning, and agentic AI fields. The registration link is right in the description below. So now let's dive into the video.
What is the sequential data? Sequential data is the set of data points that are collected, listed, or arranged in order. The order matters and typically represents time, space, or some logical progression. Okay. So suppose if I am telling you that here I love pizza. Okay. I love pizza. Okay. And if I just tell love pizza I, okay, and pizza love I, okay. So here, if you see that the text, if we all those three lines are having same words, right? Like I love pizza, in that I love and the pizza, in all those three sentences, we are having the same words. But when we place all those words in different orders, okay, so the meaning of that order will become it will changed, okay. Sometimes it will be meaningless, okay, sometimes it will be meaningless, right? So the data, if we place that data in some particular order, and if the order matters, okay, so that kind of data is called as sequential data. So there are two types of sequential data are present. One is the textual data, okay, and another is the time series data. Another is the time series data. Okay, one is the textual data and another is the time series data. So in the time series, uh, every you can say the data points are arranged in a fashion that it belongs to some specific time. Okay, so that event is occurred in some particular time. So the value of time will be milliseconds, nanoseconds, okay, then seconds, minutes, hours, days, weeks, months, quarters, years, okay. So any you can say the time frame you can observe the data, okay. So the most of the you can say the IoT devices works in the time frame of the milliseconds and the nanoseconds, okay. And most of the things also work for the in the range of the seconds, okay, and in the minutes as well, right? So if you are doing some analysis on the stock market, so there you will find the for the analysis we are having different you can say the time frames, right? Like the minutes is there, 2 minute chart, 4 minute chart, 5 minute chart, 10 minute charts is there, right? Hourly chart, 4 hour chart, then you are having the daily, weekly, monthly, and yearly charts, right? So you can observe the data in any you can say the reference of the time, but you know that that time never arranged in a distorted format. Okay, you know that after 1 p.m. 2 p.m. will come, right? After 2 p.m., 3 p.m. will come. Okay, it never happened that 3 p.m. will come before the 2 p.m., right? It will never happen. Similarly, Sunday always come before Monday. Okay, it will never happen that the Sunday occur after Monday. Okay, it never happen. Okay, since here the sequence matters, so this kind of data considered as a sequential data. Okay, now here in the time series, okay, we do so many, you can say, the analysis. Okay, so the application of the time series is like the weather forecasting, financial market analysis, demand forecasting, energy forecasting, right? So these kind of, you can say, applications that we perform, okay, in the time series analysis. Now here, mostly what happens, we are considering the single value column, okay, like this. Okay, so here we will be having the data related to the time, okay, and the amount of data. Okay, so mostly we are having this kind of structure, okay, that we consider for the time series analysis. We don't consider the multiple factors. Okay, we mostly consider the target column only. Okay, and when we are having you can say the only single target column, okay, so that is called as series, right? That is called as series. So the series that is related to the time, and if you are doing the analysis regarding that one, so that is the time series analysis. Now here the frequency of the time will be different. As I told you, it can be second, millisecond, nanosecond, okay, hour, minute, okay, year. So we consider this as a T1, T2, T3. Okay, we consider this as a T1, T2, and the T3, T4, right? So after T1, T2 will come, after that T3 will come, and T4 will come. Okay, so in this way, the sequence of the time will go in the forward direction, and at that particular timestamp we will be having some value of y, like here this is the y1, okay, this is the y2, this is y3, this is y4. Okay, at that particular timestamp, at that particular timestamp. Okay, and in the time series data, what happens, the previous value always depends upon sorry, the current value is always depends upon the previous value. Okay, the current value is always depend upon the previous value. Okay, so here the relationship between the current value, that will be created like this. Okay, so here if you see that for the current timestamp, if we consider, the value will be varying like this. Okay, so here it is the dependent variable and this one is the independent variable. Now if you observe this equation here, okay, if you observe this equation here, so we have used this equation for the linear regression. Linear regression, right? The equation for the linear regression was like this: y hat equal to beta naught plus beta 1 x1, right? Or x. So here x was called as the independent variable and y was called as the dependent variable. Now in this equation, if you see that the current value of the y depends upon its own previous value. Okay, its own previous value. So that means the value of y depends upon its own value. That means the value of y depends upon its own value. That is why this equation is called as auto regression. This equation is called as auto regression equation. That means the value of y depends upon its own value. Okay, so you can say the current value depends upon the previous value. Okay, so this is called as auto regression. This is called as auto regression in the simple manner. Okay, now it is derived from the equation of the line. Okay, it is derived from the equation of the line. So many a times it will be asked that if both the equations are same, if both the equations are same, then can we use the linear regression for the time series analysis? So we can say that yes, we can use the linear regression for the time series analysis, but the only condition is that we need to sort the data according to the time only. Okay, so if we sort our data as per the time, and if you want to predict the future, okay, so in that case we can use the regression. Okay, now there is a difference between the prediction and the forecasting. Okay, there is a difference between prediction and the forecasting. So whatever may be the prediction that we are going to do in the time series, that are called as forecasting. And if we are doing some prediction on the unknown data apart from the time series, that are called as a prediction. Okay, so in the forecasting, we are calculating the future values, right? In both the cases we are calculating the unknown values, but here in the forecasting we mainly deal with the future values. Okay, we mainly deal with the future values. And in the prediction, in another, you can say, the algorithms of the machine learning, all the values belong to at any point of time. Okay, so it doesn't matter that when the event was occurred. Okay, so it is independent of the time, so it is the prediction only, simple prediction. That is, we are just getting the values on the unknown data. Okay, but here we are mostly uh, forecasting the values for the future. Okay, for the future. So from this we can say that or we can forecast what will be the temperature of tomorrow, right? And what will happen next year or in the next quarter. Okay, so all the values that we are predicting over here in the future, so here we are doing the forecasting only. Okay, now what, there are so many different, you can say, the components of the forecasting. Okay, so these are the components: trend, seasonality, cyclicity, and the noise. Okay. Now, what is trend? Trend is long-term movement in the data. Okay, long-term movement in the data. So suppose if we are observing the data at some specific time frame. Okay, and there we are comparing its initial and the final value. Okay, so based on the values that we are observing, so we can say that it is following some particular trend. Okay, it is following some particular trend. So if the initial value is the smaller and the final value is larger, we can say that this is the uptrend. This is the uptrend. If the value, the initial value is larger and the final value is smaller, in that case we can say that it is following the downtrend. Okay, it is downtrend. And if the initial value and the final value are almost same, okay, like this, so we can say that there is no trend present. Okay, there is no trend present. Okay, so you need to observe the data in some particular time frame. Okay, and based on the initial and the final value, you can say what kind of movement your data is having. Okay, it is following. Okay, now another component is called as the seasonality. Okay, now the regular and the predictable patterns that repeat over a fixed period. Okay, over a fixed period. Okay, so that comes under the seasonality. So here we can say that the traffic is always low on Sunday. Okay, it is always low on Sunday, since no working is happening, and the Sunday is the holiday always. So you can follow this pattern that on every Sunday we are having the lower traffic. Okay, since it is following the fixed period. Okay, so Sunday comes after 7 days. Okay, the next Sunday will come after the 7 days, right? So every 7 days the traffic will be less on the road. Okay, So this is the same pattern which is occurring on every Sunday. Okay, so this is the fixed period. As well, you can say that the sale of the ice creams and the cold drinks, okay, is more or higher in the summer. Okay, so in every summer you will be getting the higher sale of the cold things, right? And in the winter we are having the higher sale of the umbrellas. Okay, so it is following the same, you can say, the pattern, and that pattern is repeated over a fixed period. So that is called as seasonality. That is called as seasonality. Now, cyclicity is also, you can say, the pattern, okay, that is repeating, okay, but there is no fixed interval. There is no fixed interval, okay, like the business cycles and the recessions. Okay, so you can say the previous recession was happened in 2019, right? Before that it was happened in 2008. Before that it was happened in 2000, right? Before that it was happened in 1990, right? So here if you see that there is a 10 years gap, okay, here it is a 8 years gap, and here it is like the 11 years gap. And currently also the recession is happening since 2024, so here it is a 5 years gap. So in the you can say the recession, the economic condition of any country is down, right? So no sales, GDP falling, right? So this kind of pattern happens there, okay, every time in the recession. But if there is no fixed interval there, so this comes under the cyclicity. Okay, now the next component of the time series is the noise or the irregularity, okay, or you can say the random variation. Okay, so if there is a random variation which cannot be explained by the trend or the seasonality, so that comes under the cyclicity. Okay, so the wars that are happening, right? And like the tsunami is there, okay, and if earthquake is there, if there is like a sudden the weather disruption, okay, if this kind of events are happening, that comes under, you can say, the irregularity. Okay, so there are four components of the in the cyclicity. There is no, you can say, the regular pattern. In seasonality we are having the regular pattern. Okay, you need to search the cyclicity with context to the time series. Okay, because in if you are searching cyclicity in context with the you can say the electronics, okay, so it is showing you the sinusoidal curve and the cosine curve there. Okay, so you need to search that in context to the time series analysis cyclicity. Okay, yes, seasonality is like a summer and winter. Okay, summer, winter, monthly, right? So Christmas comes once a year, okay, and every year it comes on 25th of December. Okay, so this is the seasonality. From 25th December till near 1st January, there is always the rise in the sale at the tourist places, because this is the summer, sorry, the holiday period. Okay, so this kind of you can say the seasonal pattern which occurs at the fixed period of time, that is seasonality. And if there is no fixed period of time or the interval, then it is the cyclicity. Okay, so the data points which are like collected, listed, or arranged in order, and the order is matters. Okay, so if we distort the matter order of that particular data, then there will be no meaning remains, right? So that kind of data is called as sequential data. Okay, so there are two types of sequential data: the textual data and the time series data. So I given you this example: I love pizza, I, and pizza love I, right? So here, if you distort the position, or you can say the sequence of the words, or place the words at different like arrangements, so if it is following the correct sequence, then and then only it will be the meaningful, otherwise it will be meaningless. Similar to the time, uh, every data is arranged in a sequential manner, okay, and there are a different frequency of the time, whether it is a nanosecond, millisecond, seconds, right, and then minutes, hours, days, weeks, months, quarters, and the years, right? So there are different frequency of the time, you can say. Okay, so if you want to observe the data in that particular time, so we are having this time series analysis. Okay, now time series analysis follows the auto regression, which is similar to the linear regression. In the auto regression, we can say that the future value of the target is depends upon its own past value. Okay, so this is the auto regression. Now we discussed about the components of the time series. So in that there are components. Okay, the trend. So trend shows the long-term movement in the data. Trend can be upward, downward, or there will be no trend. Okay, in my data, and there is a seasonality. So if the pattern repeats over a fixed period of time, then we can say that there is a seasonality. Okay, so the time frame there can be anything. Okay, it can be like the minutes or the hours or the days or years, right? So but the interval of the time is fixed. Okay, cyclicity, here the pattern repeats, but there is no fixed interval. Okay, so in that case we can say that it is a cyclicity. And in the noise or irregularity, we can say that there is no explained variation by the trend or the seasonality. Okay, so anything can happen anytime. So sudden weather disruptions, tsunami, wars like situation, right? So this comes under the noises. Okay, now in order to complete the time series analysis task, we need the stationary data. Okay, so the stationary data is the data which don't have any trend and there is no seasonality. Okay, so we need to do the stationarity check. Okay, we need to do some stationarity check in case of you can say the time series. Okay, so there are multiple ways to check the stationarity. Okay, so either you can check visually that you any trend persist in your data or not. Okay, or you can do some the simple statistical check, like you can check whether the mean value, okay, it is changing over time or not. Okay, and if variance is changing or covariance is changing over a period of time or not. And there is another more statistical way to check the augmented Dickey Fuller test. Okay, now when you are checking whether the seasonality is present in your data or not. Okay, so for that what we do, we decompose the entire, you can say, data into different components. Okay, so here if you see that we are having the the observed pattern of the data. Okay, now from this we want to extract the information like the trend and the seasonality and the residual. Okay, so for that purpose, we do the uh, time series decomposition. Okay, for that purpose, we do the time series decomposition. So because of this decomposition, we see different models. Okay, different models. Okay, like if you want to just observe what is the trend. Okay, so this is extracted information from the observed information. Okay, now if you just want to know the seasonal pattern. Okay, And if you just want to know the random noise pattern there, okay, so for that purpose we will be having this kind of, you can say, the time series decomposition. Okay, so from here we can say that there is a trend present in our data, right? There is a seasonal pattern here. If you see that the data is, the pattern is repeating, right, for each and every year. Okay, so here as well we can see that the pattern is getting repeated, right? So there is a seasonal pattern present in our data. So visually you can compare that there is the trend and the seasonality present in our data. Okay, so there are two types of decomposition model. One is called as additive model, and the second is called as a multiplicative model. Okay, so in the additive model, what we do, so we add all the components, okay, like a trend plus seasonality plus residual. Okay, and in the multiplicative model, what we do, we multiply every you can say the components like trend into seasonality into the residual. Okay, now this additive model is used when the variation, a seasonal variation is constant over a time. Okay, so here you can see, if we find that there is a variation in the seasonality is constant, so for that we will be using the additive model. Otherwise, if the seasonality is increasing like this, okay, if the seasonality is increasing like this, okay, and if there is like the exponential growth in the trend as well, okay, so for in that case we will be using the multiplicative model. Okay, so this is the time series decomposition model only. Okay, most of the time what we do, we will be using this additive model. Okay, but if there is a sudden or you can say the exponential change in the pattern, so for that we will be using this multiplicative model only. Okay, now there is one more you can say the stationarity check, that you need to check the mean value. Okay, mean value for different time frames. Okay, so suppose if you divide this you can say the trend, okay, or the observed value in different time frame like this. Okay, so you need to check what is the mean value over here, 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 and what is the mean value over here. Okay, now if you found that if this mean value is not showing any change, like if you are having mu1 equal to mu2, right, equal to mu3, okay, equal to mu4, okay, and equal to mu5, then in that case you can say that your data is stationary. In that case you can say that your data is stationary. Otherwise, if there is a change in the value of this mean, okay, so you can say that your data is non-stationary. Okay, so this is also like a method to check the stationarity or the non-stationarity in your data. Okay, now if you want to check by the standard statistical method, so there is like the method is called as augmented Dickey Fuller test. Okay, so Dickey and the Fuller are two different scientists. Okay, so here the augmented Dickey Fuller test is say that or it is used to check whether the time series data is stationary or not. Okay, so here we set some hypothesis, null hypothesis and the alternate hypothesis. So the null hypothesis says that the series has unit root and it is non-stationary, and the alternate hypothesis says that the series is stationary. Okay, now while performing this augmented Dickey Fuller test, we check the value of p. If the value of p is smaller than 0.005, then we reject the null hypothesis and we say that the series is stationary, else we say that it is non-stationary. Okay, now it is very important or it is the only one assumption of the you can say the time series, you can say that we require the series to be stationary. Okay, we required a series to be stationary. If the series is not stationary, then we like try to make that series stationary. Okay, so I will first explain how we can do this in the you can say the Python, okay, and then we'll see the next topic like differencing, how this differencing work, okay. You need to perform the differencing operation. Now how this differencing operation work? So here it will do this calculation, okay. So yt minus 1, okay. So this is the first order differencing, okay. So here we are considering the first lag. Now how this will perform? So what it will do, it will consider the current value and it will subtract the previous value, okay. So suppose if we are having this is the y column, okay, this is the y column here. Now for this y column, these are the different values, right? So here it is the y1, this is the y2, this one is the y3, okay. Now if you want to calculate the differencing for this y1, okay, so what you can do over here, like y1 minus, okay, so previous value of y1 like y0, okay. So t minus 1 is nothing but the, if we consider t equal to 1, then t minus 1 will be 0, right? So here y1 minus y0. So before this y1 we don't have any value. So when we calculate the differencing, the first value will comes as a nan value, okay? First value will be the nan value. Now the second value here, it is y2 minus y1, okay. So y2 minus y1, so here you can see 118 minus 112, the value is 6, okay. So we continue for this. Now after calculating the first differencing, we again apply the augmented decay Fuller test on that differencing column, okay. So if it rejects the null hypothesis after doing the first differencing, then we can say that we are getting the differencing value as a 1, okay. We are getting differencing value as 1, okay. If suppose it accepts or fail to reject the null hypothesis, in that case what we'll do, we'll perform the uh, 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 second, you can say, differencing there, okay. Here we are performing the second differencing. Now here what it will do, it will consider the equation like this, yt minus yt minus 2, okay. So what it will do over here, so suppose if we are calculating for this y3, okay, so y3 minus y1, okay, because here the value of t is what, 3. So t minus 1 will be sorry, t minus 2 will be what, 1, okay. So here we are having 132, okay, and 112. So when we do this differencing there, so we will be getting value 20, okay. So from there we will be calculating the second differencing column. Now after calculating this, again we will be applying this augmented decay Fuller test on this you can say the column, okay. Now if it is like rejects the null hypothesis there, so we can say that we are having the value of d equal to 2, okay. We are having the value of d equal to 2, okay. So this is the differencing value. So there is a significance of these differencing values, okay. So for that we will be using this differencing value in our forecasting model, okay. Now as we are having the stationary data, okay, as we are having the stationary data, so for that we can say that we don't require any differencing, therefore we will be having d value equal to 0, okay, because our data is already stationary, so we are not performing any differencing operation, okay. So in order to make the data stationary and in order to check the date stationarity differencing value, so for that purpose, we will be using this differencing method. Okay. So we will be applying that differencing. Now, where do we using this differencing value? So we are using that differencing value into different, you can say, the forecasting models. Okay. So we will be having these forecasting models. Okay. In order to forecast the future values. So here the first value is ARIMA. Okay. So there are multiple flavors of this ARIMA. Okay. So these are also called as the box Jenkins model. Box Jenkins model. So there is a model called as ARIMA. Then there is SARIMA. and one more there is SARIMAX. Okay, so there are three, you can say, the flavors, you can say, for this box junction model. So okay, so here we'll discuss about this ARIMA and the SARIMAX. Okay, ARIMA and the SARIMAX. So ARIMA is nothing but auto regressive. Here AR term is the auto regressive, I term is integrated. Okay, I term is the integrated, and MA is nothing but the moving average. Okay, so autoregressive integrated moving average. Here S stands for the seasonal. S stands for the seasonal. Okay, seasonal autoregressive integrated moving average, and here X stands for the exogenous components. Okay, exogenous components. Okay, so here it will become seasonal autoregressive integrated moving average exogenous regression. Okay, so these three models. Okay, so here we required three, in the ARIMA we required three components. Okay, so autoregressive component, then the integrated component, and the moving average component. Okay, so here we will be using this ARIMA. Okay, so the second is the exponential smoothing. So exponential smoothing, it is using the weighted average of the past observation where the weights decrease exponentially. Okay, so this, there are three types of this exponential smoothing. One is called as simple exponential smoothing, Halt's linear trend, and the Halt Winter exponential smoothing, where we will be considering the trend and the seasonality there. Okay, now the third is we are using these neural networks. So the simple neural network that we are going to use is the RNN, that is the recurrent neural network there, and the LSTM, which is the flavor of the RNN. Okay, so long short term memory, that you can say the forecasting model is there. Okay, apart from there, the Prophet model is also there. Okay, Prophet model is also there. So we are not going to see that Prophet model. We will be focusing more on this ARIMA, SARIMAX. Okay, ARIMA, SARIMAX, and the LSTM. Okay, LSTM. So three model we will be seeing in the detail. Okay, now how this ARIMA model work? Okay, so how this ARIMA model work? So ARIMA is having, you can say, the three components there. Okay, there are three components. So the three components are nothing but the auto regressive, integrated, and the moving average. So here we have just seen how to calculate the differencing. Okay, how to calculate the differencing. Now here in this stationarity check only, so I had told you that we are using this differencing method, and we are going to check after how many differencing we will be getting the stationarity in the data. Okay, so suppose if our data is already stationary, then we are having the value of d is equal to 0. If our data is not stationary, then what we do, we do the first differencing. Okay, and then again we check by using this augmented decay Fuller test whether our data becomes stationary or not. If in the first differencing only we are getting the stationarity into our data, then we can say that we are having differencing equal to 1. If in the second we are having the stationary data, then we can say that value of d is equal to 2. Okay, so here in our case we are having the value of d is equal to 0. Okay, value of d is equal to 0 there. Okay, now there are two more terms, that is the p and the q term. Okay, so we require this p, d, and q. Okay, we require this p, d, and q in order to put the values while using this ARIMA. Okay, so p, it is used for the auto regression part. Okay, so it uses the past values in order to predict the future values. As I told you that the current value of the you can say current value of the y depends upon its own previous value. Okay, so it is like the first previous value, second previous value, third previous value. Okay, so this is the auto regression equation. Okay, so here we required this value of p there. Okay, we required value of p there. Okay, so it is telling us that by how many value, how many previous value that we consider. Okay, for the current value. Okay, so there is another method. It is the another you can say the component is the moving average component. Okay, and this is the equation for this moving average. Now here the output depends upon its past errors. Okay, now this output depends upon its own past errors. So here the mu is nothing but the mean value. Mu is nothing but the mean value. Okay, so what it will do, suppose if we are having the data like this. Okay, so here y1, y2, y3. So the mu will be the mean of y1, y2 and the y3. Okay, so for entire data we are calculating the mean. After that we'll be like adding the error terms. Okay, error terms for each and every, you can say, the timestamp. Okay, so this component is called as moving average component. Okay, so moving average doesn't mean over here that we are doing the exponential smoothing over there. Okay, so here we are just adding the mean term there, and after that error term are getting added. Okay, so how to find the values of this p and the q? Okay, how to find the values of the p and the q? So there is a library that is available in the Python. Okay, so that will do our job there. Okay, so it will do the permutation and the combination, and then it is try to extract the best value of the p, okay, and the q. But if you want to find the values on your own, so there are two, you can say, the plots that we need to use. One is the ACF plot and the second is the PACF plot. Okay, so what is ACF? ACF is nothing but autocorrelation function, and PACF is partial autocorrelation function. Okay, ACF is autocorrelation function and PACF is the partial autocorrelation function. So what we are going to do over here, we are just plotting this kind of lollipop plots. Okay, so this kind of lollipop plots that we are going to plot, and we are using some you can say the interval value. Okay, now this lollipop plots, it is plotted in on the y-axis. We are having the autocorrelation and the partial autocorrelation values. Okay, so this autocorrelation or the correlation value, we know that the range of that correlation is varying from -1 to 1. So for the -1, we say that it is highly correlated in opposite direction, and for 1 we say that the data is highly correlated in the positive direction. That is, if some data is decreasing, then another value is also decreasing, and here we can say that if some value is increasing, then the other value which is correlated to that value will also increase. Okay, so we know that the correlation, right? So here as well we are having the maximum value 1 and the minimum value is -1. So in between this range only we are plotting the plots. Okay, now here we are just mentioning the number of lags. Okay, number of lags, that for how many lags we are going to use. Okay, so lags means what? So suppose if we are using the lag value as 1. Okay, for lag value as 1, so we will be considering yt. In order to calculate the yt plus 1, we will be having yt value. Okay, after that we will be having yt minus 1 value. So here we are just considering the 1 previous values. Okay, so we are having lag 1. Suppose if we are having lag 2 there. Okay, suppose if we are having the lag 2 there, so how this lag 2 you can say considers? So here if we are having lag 2, then for this yt plus 1, we will be having the value like yt minus 1. After that we are having values like yt minus 3. Okay, so we are just considering the previous one skipping and the previous values. Okay, so in between, so in this way we will be like using this lag. Okay, so here for the lag 1, lag 2, lag 3, up to how many lags that we decide, this is the hyperparameter that we are going to use to plot this ACF and the PACF plots. Okay, now this ACF and the PACF plots will give us this kind of, you can say, the plots. Okay, which will look like this lollipops. Okay, so which will look like this lollipops over here. This is the lollipop. Okay, so this one is like this. Okay, now there is, you can say, the confidence interval that is present like this. Now we need to skip this one. Okay, we need to skip the first one. So the first one we are going to skip, because in the first lag it is correlating with itself only. Okay, so suppose if we are checking for the yt value, then it will be correlating with itself only. Okay, so yt value only. Okay, so the we are going to skip the first lollipop. Okay, after that the value, or the you can say this vertical line, or you can say the lollipop. Okay, so where it is coming inside this confidence interval shadow. Okay, so that part we will be considering as the uh, p- q value. Okay, so here, okay, so here we can see that in the ARIMA we are having this p value there. Okay, and here in moving average we are having the q value. Okay, so ACF will give us this Q value. Okay. ACF will give us the Q value, and PACF will give the P value. Okay. So here ACF will give the Q value and PACF will give us the P value. Okay. P value. Now, how this P value and Q value is considered? So in this region only. So suppose this one is the first lollipop after the initial lollipop, which is comes inside the this region. Okay, so we can say that here we are having q equal to 1. Okay, q equal to 1. Okay, now suppose over here as well. Okay, so whenever we are going to calculate the value of the p, so we don't consider the first lollipop there. Again, after that we are checking after how many lags the value is inside the shadow. Okay, shadow region. So here you can see here as well, this comes inside the shadow region, right? So we can say that here we are having the p value is equal to 1. Okay, now for our data we are having d equal to 0, p equal to 1 suppose, and the q equal to 1. Okay, now by considering these three values, because our data is stationary and we haven't done any differencing, therefore we'll consider that d is equal to 0 there. Now we consider this p, d and q value as 1 0 1. Okay, so this combination will try. Okay, and after that we'll try to do the forecasting. Okay, now if the forecasting is very closer, then we'll finalize these you can say the pdq values. Okay, now suppose if we don't find that our the value, that is, suppose if we are having some values of the y over here. Okay, so these are the actual value y1 y2, and these are the predicted value y hat 1 and the y hat 2. Suppose if there is very small difference between this y1 and y2, sorry, y1 and y1 hat, y2 and y2 hat. Okay, then we will stick to the our initial pdq combination. Okay, we'll stick to that our pdq combination. Now if there is a large difference between the forecasted value and the actual value there. Okay, so what we'll do, we'll consider another combination. Now we'll move again in this direction. Okay, so after failing to predict the actual the closer value, what we need to do now, we need to consider the different value of the q. Now here if you see that this lollipop is outside the shadow region, this is the outside the shadow region, now this one is the inside this shadow region. Now here it is 1 2 3 and this one is the 4. Now our value will become what, q equal to 4. Okay, because the fourth lollipop after this initial lollipop there, it is coming inside this shadowing region. Now for this a new combination we are having q equal to what, 4. Okay, now again over here we'll see that after this first, second and this third lollipop is inside this shadow region. So here our newer value of p will become what, 3. Okay, so the new combination of this p, d and q will become 4, sorry, not 4, it is 2, sorry, it is 3. okay, because here the third lollipop is inside the shadow region. 3, 0 and 4, okay, P, D and Q. This new combination will be there. Now what we'll do, we'll again try to forecast the value. Again we'll check that the actual value and the forecasted value are both are closer or not. Okay, if both values are not closer, then what we'll do, we will be like finding for the new combination there. Okay, finding for the new combination there. Okay, so this is, we need to check. Okay, we need to check for the values of the P, ACF and the PACF value. Okay, now these plots, okay, ACF and PCF plots, that will be like a very easy. Okay, so ACF is nothing but autocorrelation function, and PACF is, it is nothing but partial autocorrelation function. Okay, now ACF will be considering all its direct previous values, like it is considering like yt minus 1, yt minus 2, yt minus 3, yt minus 4, and so on and so forth. Okay, but if we consider that PACF value, okay, so if we are having different lag value, okay, so what it will do, it will exclude the bit the intermediate values, okay, which values that are present in between. Like suppose if we are calculating for the yt, okay, if we are calculating for this yt, now we are using this lag 3. So for lag 3 we are just referencing yt minus 3 value. Okay, we will exclude the adjacent values like yt minus 1 and the yt minus 2 there. Okay, so it is used to calculate the PSA, partial autocorrelation function. Okay, and here it is the autocorrelation function there. Now, in order to plot all those values, okay, in order to plot all those values and how we can see in the Python, okay, so this lollipop plot, and how we can automatically generate the different combination of this PDQ there. So for that, we are having different methods, okay. Auto-regressive integrated moving average with exogenous regressors. Okay, so this is the large name of that SARIMAX. Okay, so here we will be having the two components, sorry, three components. One is non-seasonal, second is seasonal, and third one is the exogenous variables. Okay, now whenever we are having some data which is depends upon the seasonal variations, like the temperature. So we know that in every season we are having different values of the temperature there, right? So for that we will be using the SARIMAX model. Okay, so here the S stands for the seasonal. Okay, seasonal, that is we are considering the seasonal pattern there. Now here in between this ARIMA is same, autoregressive integrated moving average. Okay, the same component that we are considering. And the last is the exogenous. Okay, so the exogenous is nothing but the extra features that influence the target. Okay, so sometimes what happens, the pollution hampers the temperature value, right? If the city is polluted, okay, then we can say that there will be more temperature in the city for that current day. Okay, so if you are having that kind of, you can say, the values, external values, that you need to consider. Okay, so these external values, you need to calculate first. Okay, you need to get the extract after the calculation, and then you could form a list of that exogenous variables, and then you will considering all those along with the SARIMAX. So since in our model we don't have this exogenous, okay, and again we are using this SARIMAX only. So for that we will be considering the seasonal part and the non-seasonal part there. Okay, so in the seasonal part we are considering the normal PDQ values, that is the autoregressive integrated and the moving average values. And in the seasonal part we are having capital P, capital D and capital Q. Okay, so capital P is nothing but seasonal autoregression, D is seasonal differencing, Q is seasonal moving average. Okay, and here the seasonal period. Okay, so here we are having the 12-month season. Okay, so that's why we will be considering 12 over there. Okay, so here if you see in our you can say the data. Okay, sorry, in our model, that is the exponential smoothing. Okay, exponential smoothing. Now here we will be considering this Holt-Winter model because our data was showing some smaller trend there and the larger seasonality. Okay, so there are three types of the exponential smoothing model. One is simple exponential smoothing. It is considered when there is no trend or the seasonality. Holt linear trend when there is only trend, no seasonality. And Holt winter model when there is a trend and the seasonality, both are present. Okay.
And that's a wrap. We have covered the fundamentals of sequential data and time series analysis, diving into how trends, seasonality, and noise shape predictive models like ARIMA, autoregression, and exponential smoothing. So whether you are aiming for roles like data scientist, AI engineer, or machine learning developer, mastering time series forecasting and predictive modeling is essential for making accurate, data-driven predictions in any industry. And if you are ready to take your AI skills to the next level, don't miss out on our free 90-minute masterclass. So register now through the link in the description below. And thanks for watching and stay tuned for our next video.